All right, welcome back. We'll now talk about a little bit of like generic signature stuff, I guess. So the first point that I want to talk about is using hash functions to kind of compress the public key. So if you, for example, remember the Lamport signature scheme, there the public key is like really huge. And now I want to present like a easy and kind of stupid idea to make the public key shorter, which is just hashing the public key. And then just publishing this hash and then using this. Okay, so let's be a bit more concrete about this. We take some hash function pih and a base signature scheme pibase. And then we construct a new signature scheme, which kind of written down looks more complicated than it actually is. So the idea is that the public key of this new scheme consists of a hash of the public key of the old scheme and the hash key. And then when I sign a message, I basically compute a new signature as before. And now I'm additionally publishing the full public key within the signature. So basically I'm now, I made the public key pretty short because now it's just a hash of the public key, of the original public key. But now my signatures are much longer because each signature now contains like the full public key. So that's kind of a stupid trade-off, but we just do it as an example to be able to prove something. Then when I verify the signature, I make sure that the public key included in the signature is actually has the same hash value as up here. And obviously we verify the signature. So let's prove that this is actually still secure. One reason why it may not be secure is that if we allow the adversary to include the public key under which the signature should be valid, if we allow him to kind of come up with this public key himself and just include it in the signature, then obviously he would be able to break this whole scheme, because coming up with your own public key and a valid signature for that is not that hard. However, the idea is that he shouldn't be able to do this because the public key that he comes up with needs to have the same hash value as the public key that we generated in the beginning, this one. So through this, we should be able to kind of argue that the adversary has two ways of breaking this whole scheme. He can either come up with a new public key, but then he would break the collision resistance of the hash function, because now he has like this hash collision here. Or he can use the same public key that we used in the beginning, but then he would have to forge a signature for our public key, which should be not possible. So you've already seen the proof for hash then sign in the lecture, and this one is actually kind of similar. So take a moment, think about how you would structure this proof for this scheme here, and well, then I'll see you in a second and we'll talk about it. All right, so the nice thing with like the hash then sign proof and also this proof is we have this one very clear case distinction. In case number one, the adversary finds a collision for the hash function, and in case number two, the adversary forges a signature. And the nice thing is that we can very clearly state when we are in case one and when we are in case two. So let's define an event that kind of distinguishes the two cases. And that event, let's call it collision, because it's kind of as in the hash then sign proof. Which is that if the adversary in the end outputs a forgery like this, then the event collision says that the public key that he's using here is not the same as the public key that the challenger generated, so not the same as PK base, but the hash values are the same. And then we can do the standard case distinction as we usually do with the probabilities. So we basically we divide this probability into those two cases where either a collision happens or it doesn't happen. Now we want to show that this is negligible, and we can do this in two parts. We show that this is negligible, and we show that this is negligible. How do we do that? Take a second, think about it. So yeah, we start with this thing. And well, the idea is that this probability should be small because the probability of a collision happening should be small, right? So what we would do would be a reduction. We construct a new adversary A prime against the collision resistant hash function. A prime essentially plays the role of the challenger for A. What he will do is generate a key as usual, but he will use the hash key that was provided by his challenger. So A prime that we're constructing right now is playing against the collision resistant hash function. So as input, he gets this hash seed S, this hash key S. So instead of generating it normally, he would just embed the S that he gets as input into the public key of the whole signature scheme pi. And then he just runs A through this experiment, doing everything that an honest challenger would do. And then at the end, he would just output this hash collision that we have here. So if there's a hash collision, then he outputs it. And now the chances of this A prime winning is exactly the chances that like this collision event happens. So this probability here is at most the probability that like A prime wins. And then this is negligible because it's a collision resistant hash function. The other thing is that this event happens and there no collision happens, which means that in particular the public key that he gives us a forgery for is the same public key as was used by the challenger. So for this reduction, we come up with an adversary A prime prime, which plays against the original pi-based signature scheme. Basically, he would now generate this AS here honestly, but he would, instead of SK base, PK base, he would use the things from his challenger. So he plays against the signature scheme. So he would get the public key of his challenger. And he would basically compute the public key for A by hashing the public key of his challenger. So PK base. Then A will do queries. These queries obviously cannot be answered by the adversary A prime prime directly because he doesn't have the secret key for SK base. But he can, instead of computing the signatures himself, he can obviously just query them from his challenger. He would then get these sigma bases, and the PK base he knows anyway. And then in the end, he would just output the message signature pair that A outputs and hope that it's a valid forgery. And so if this event happens here, the A wins and there's no collision, then this thing that A prime prime outputs is actually a valid forgery for PK base, so for the public key, which it doesn't have the secret key to, which it shouldn't have been able to do, meaning that this is also negligible. All right, and this is like the whole proof. It's kind of the same as the hashed and sign, because we had this collision event, where also we construct an adversary against the collision resistant hash function that was able to kind of win very easily if this collision event happened. If in this proof the collision event didn't happen, then you would know that the hash value that was used in the signature is new, and so you could claim a forgery for the inner signature scheme there as well. It's just a broad idea. And here it's kind of the same. So it was kind of a nice exercise to do this. So while the construction we've just seen is not all that interesting in practice, it's kind of stupid. This one is much more viable. And what we want to do is we want to have shorter secret keys. And essentially we can think about as doing this in two steps. First of all, as the secret key, we don't actually store the secret key, but instead we store the randomness that's used to generate the secret key. Okay, so the key generation algorithm always takes, like implicitly does some coin tosses, and we have this notation that we give it randomness explicitly as input, and we just store that randomness. And then whenever we actually need the secret key, so the actual secret key, not just the randomness that's used to generate it, we would just generate this secret key, or like recompute the secret key using this randomness again. And as soon as we have this, basically we are pretty good, because now our secret key is just a random string, and we know very well how to compress random strings, because we know how pseudonym generators work, and they are really good at doing this. So what does this construction do? When generating a key, the construction will generate a secret key and public key, kind of as usual, using the key generation algorithm of the base signature scheme. But instead of actual randomness, it will give it just pseudo-randomness. So G of R for some R that's randomly chosen. And then the public key is the normal public key, and the secret key is just the randomness that was used as input for the pseudorandom generator, and then ultimately as input for the key generation. So then verification works as before, so there's no change. The public key is still the same, and signatures will still look the same. But when we're signing a message, we need the secret key, so the actual SK base from the base signature scheme in order to create the signature. And essentially, we just stored this R that we used to generate it in the key generation. So now what we're doing is we are doing exactly the same process again, and generate the public key, secret key anew. So we don't have it stored, but we can now generate it new. We are using the same randomness as before. So the key gen algorithm of the base signature scheme will output the same key pair as before. So in particular, we get the same SK base as we had here. That's fitting for PK base, and then we can use that to send to create the signature. So the punchline is we just store essentially the seed for pseudorandom generator, and then we as the secret key, and whenever we need the secret key, we just generate it anew by running the keygen algorithm with the expanded seed as randomness. So, assuming this G is a secure PRG and the base signature scheme is secure, then I claim that this scheme that we've just constructed is also secure. Take a second, think about what the proof outline would look like. So what kind of proof you would have to do, what's kind of the rough idea of how this is going to go. And then, yeah, just pause the video, then we'll talk about it. All right, so what we want to do is we want to show that any adversary A has negligible chance of winning against this newly constructed pi scheme. So and the rough idea will be that this scheme pi base is secure by assumption. And pi and pi base, they're only different in the sense that one uses pseudo-randomness to generate keys, and the other one uses like actual randomness. All of the other stuff, like from A's perspective, because A only sees the public key and the signatures, all of those are distributed exactly as before. So what we're doing is we're constructing a distinguisher against the PRG. So in this construction, the distinguisher that we're constructing, it will play the role of the challenger in the signature game against the adversary A. And then it behaves as the challenger would, except that whenever it calls gen base, it will use its own input, which is either, if you remember, this is either pseudo-random or random. And now we do the standard analysis. And then basically the idea is that if the input of D is pseudo-random, then for A, everything looks like it's playing against the scheme pi. So all of the keys are generated with pseudo-random inputs. If the distinguisher gets properly random input, capital R, then for A, everything looks like it's playing against the original scheme pi base. And then the distinguisher that we're constructing should output to 0 or 1, kind of guessing in which one of those worlds it is. So what we're doing is we're outputting this bit indicating whether or not A wins. Then the idea would be that if A is able to win more in this one world than in the other world, then we would output different bits in those both worlds rather frequently. So then standard analysis applies. And then we're essentially done because we know that these two here are close, so their difference is negligible. And so also these two are close, so their distance is also negligible. And then we know that This one here is small because pi base is a secure signature scheme. So overall, we also get that this is small, and this is what we need to show. So the probability that A wins against our newly constructed signature scheme is negligible. Okay, so finally, let's talk about one-way functions and digital signatures. Essentially, what we're doing in the lecture is we show that from one-way functions, we can construct digital signatures. So one-way functions are sufficient for constructing digital signatures. And now what we can think about is, do we actually need the existence of one-way functions, or can we do something less? Can we get away with an even milder assumption? Essentially, the answer will be no. What we can show is that one-way functions are not only sufficient to construct digital signatures, they are also necessary. What we can show is that if secure digital signature schemes exist, then also one-way functions exist. And how do we show this? We take an arbitrary secure digital signature scheme, and then we construct from this a one-way function. Okay, think about it for a second yourself, and then we'll talk about it. So as soon as you have the idea, it's actually not all that difficult anymore. The rough intuition is that in a public key scheme, we have a public key and a secret key. And we have to have that from the public key, it's hard to compute the secret key. And this is kind of the one-way function. So assume we had a key generation algorithm that first generated a random secret key and then constructs the public key that belongs to that. Then this key generation algorithm would be a one-way function, right? So random input, random secret key. And then from this random secret key, it's easy to compute the public key. But given the public key, it's hard to get the secret key back. Now, the only technical challenge that we have left is that we don't actually know whether our key generation algorithm actually works like this. However, we can basically apply the trick that we had in the construction before, which is essentially that we can always just replace the secret key with the randomness used to generate the public key secret key pair. And so overall, the actual one-way function that's always present in signatures is that maps randomness R to the public key generated by the key generation given randomness R. And let's just assume that like the R has the correct length. I'm pretty sure you can fix this by just scaling the security parameter correctly. And so I claim that this is a one-way function. Do you have an idea how to prove this? The idea is that we define, so we assume we have an inverter against the one-way function. Then we construct an adversary against the digital signature. Then essentially what we're doing is we get the public key from the challenger. Now A prime wants to use A. What is A good at potentially? It's good at inverting the one-way function. So we'll give it the function value pk, and we will get some kind of R back. And now what A can do is just, well, essentially now using this R, if this is actually a pre-image for this one-way function, then it can just run the key generation again. We get the same public key as we got from the challenger, if A was able to invert the one-way function. And now we can use the secret key to just forge a signature. And because the digital signature scheme is correct, and this PK-SK combination is, well, valid output of the key generation algorithm, this signature here is correct. We haven't queried anything, so we would just win. In the end, let's say that A prime just aborts if A is not able to invert something, and then we can say that A prime wins if and only if A inverts the one-way function. So the probability for A prime winning is the same as the probability for A succeeding, meaning that both should be negligible. And there we have it. That's our one-way function. Thanks for your attention. See you in the next video.